Let's begin by erasing the postcard. That wave, a towering wall of water hurling itself onto immutable rock, is not a single entity. It is the catastrophic failure of a complex energy system. The data, drawn from hydrodynamic studies using particle image velocimetry and high-speed laser scans, shows that the moment of impact is less a crash and more a shattering. When a wave's crest finally collides with a jagged rock face, the water's velocity can exceed 30 miles per hour, but it's not moving as a solid block. The leading edge undergoes what physicists call violent fluid-structure interaction, where the water instantly decelerates from that speed to zero in a few milliseconds. This creates a pressure spike of staggering proportions, up to several atmospheres of force per square inch, a shock wave that travels back through the incoming wave itself. This is the first secret. The iconic splash is not the wave moving forward, it is the wave recoiling from its own death. The white spray and plume shooting skyward are comprised of water particles that were nanoseconds before at the heart of the wave's momentum, now being violently ejected backward and upward as the kinetic energy seeks the path of least resistance, which is suddenly away from the rock. The sound you associate with the crash, that deep, thunderous roar, is a lie your brain tells you. Hydrophone recordings from within the impact zone reveal it to be a complex cacophony, a sharp rifle crack of the initial slap, followed by a low-frequency rumble from the collapse of air cavities trapped and violently imploded within the water, and finally, a hissing sizzle of countless microbubbles collapsing, a process called acoustic cavitation that generates temperatures hotter than the surface of the sun for brief, fleeting instants within the water itself. The rock is not a passive participant. Seismic sensors placed on coastal cliffs record that every impact is a tiny earthquake. The jaggedness of the rock is critical. It doesn't simply split the water, but causes asymmetric loading, creating vortex sheets and turbulent eddies that spin off with their own miniature energy systems, literally stealing rotational energy from the wave's main flow. This is why no two breaks are ever alike. The fractal geometry of the rock surface, down to the micron-level imperfections, dictates a unique chaos pattern every single time. The sunset light further layers on the deception. The famous orange and purple hues are a product of Rayleigh scattering, yes, but when interacting with the aerosolized plume mist of water droplets and sea salt, the light undergoes scattering as well. This creates that glowing, ethereal backlighting, because the droplets are of a size comparable to the light's wavelength, scattering the reds and oranges forward toward your eye while the blues are scattered away. Your retina is capturing not the true violence, but a filtered, atmospheric rendering of its aftermath. Furthermore, the very persistence of these jagged rocks is a testament to a time scale we cannot comprehend. That basalt or granite has endured not thousands, but millions of such impacts, each one a minuscule act of erosion. Computational models simulating this abrasion, factoring in water hammer pressure, the abrasive sand suspended in the water, and the chemical withering from salt, show that the sharpest edges you see are often the newest, created by recent fractures. The seemingly timeless, rugged landscape is in a state of constant, if imperceptibly slow, reconfiguration, a dance between immense but fleeting fluid power and patient, immutable solidity. This interplay is the core drama, and we've only just begun to decode it. The wave is not breaking against the rock, it is being disintegrated by it, and the rock is being infinitesimally rewritten by the wave. It is a war of attrition where both parties are transformed in every encounter, a cycle of destruction and shaping that has continued for epochs, long before any eye witnessed its beauty. This foundational understanding shatters the simplistic view, revealing the scene as a kinetic sculpture of interacting forces, a real-time physics simulation of staggering complexity happening right in front of us, yet almost entirely invisible to the untrained UN data-informed eye. Now let's descend deeper, beneath the surface, into the realm where the wave is born. The sunset breaker doesn't originate at the shoreline. Its fate is sealed hundreds, sometimes thousands, of miles out at sea. The data comes from oceanographic satellites like Jason-3 and Sentinel-6, which measure sea surface topography with centimeter precision. They reveal that the wave that eventually detonates on your jagged rocks began as a mere ripple of energy, a transfer of momentum from the wind to the water surface. But this isn't a simple push. The process, known as the Phillips-Miles theory of wave generation, involves a complex resonance. As wind blows across an initially calm surface, it creates pressure differences on the windward and leeward sides of tiny wavelets. When the speed of these nascent waves matches the speed of the wind's forcing, resonance occurs and energy is efficiently pumped into the wave, causing it to grow. The significant wave height, the period, the direction, all are determined by three factors: wind speed, the duration for which that one blows, fetch, and the distance over open water it can blow uninterrupted, fetch length. A storm in the North Pacific, with winds gusting at 50 knots over a fetch of 500 miles for 48 hours, can generate a swell system carrying the energy equivalent of a small nuclear bomb across the ocean. This energy doesn't travel as water moving horizontally. That's a myth. The water particles themselves move in near circular orbits, their diameter decreasing with depth. The waveform, the shape, is what propagates, a phantom of energy racing at speeds that can surpass 30 miles per hour. In deep water, this is the second secret. The wave is a ghost, a traveling disturbance, not a moving body of water. As this swell system approaches the continental shelf, the shallowing seafloor begins to interact with this deep water energy. When the water depth becomes less than about half the wavelength, the wave feels the bottom. This triggers a process called wave shoaling. The wave speed decreases, its wavelength shortens, but its energy remains largely constant. With the same energy packed into a shorter, slower wave, the only direction for it to go is up. The wave height increases, steepening dramatically. This is where the specific configuration of the seabed, its slope, its contours, becomes a director of the final act. A gently sloping sandy bottom will cause the wave to spill gradually, creating a surfer's rolling break. But our jagged rocks? They are typically fronted by a steep, rapidly shallowing bathymetry, often a direct plunge from deep water. This allows the wave to maintain much of its energy and momentum until the very last moment, transforming it into a plunging breaker, the most violent kind. The wave's front face becomes nearly vertical, often curling over to form a tube before the crest collapses entirely under gravity. The exact point of break is a function of the wave's height, period, and the water depth at a given location, calculable with the number, a dimensionless parameter used by coastal engineers. But here's where organic, original data from wave tank experiments adds a critical layer. The presence of the jagged rock itself modifies the local wave field before impact. Using refractive wave models and computational fluid dynamics, CFD, simulations, scientists can show that the rock acts as an obstacle, causing wave diffraction, the bending of wave energy around the obstacle and partial reflection. This creates an interference pattern. Some waves might cancel out slightly. Others might combine to form a larger, more powerful crest just before impact. The rock is not waiting passively. It is actively shaping the very wave that is about to attack it through subtle, pre-impact interactions. Furthermore, the tidal stage is a master conductor. The same rock that causes a spectacular, high-energy crash at high tide might be a dormant, seaweed-draped pillar at low tide, with waves breaking further out. The tidal dam, the vertical reference point, changes the entire shoaling equation by several meters, effectively moving the launch point of the final break. All of this, the distant storm, the ghost-like energy transit, the seafloor slope, the rock's preemptive interference, and the moon's gravitational pull conspires to create that single, photogenic moment. It is a chain of causality stretching across planetary scales and deep time, culminating in a microsecond of explosive release. To see a wave break is to witness the endpoint of a vast, invisible journey, a telegram from a storm sent days ago, delivered with brutal force onto the anvil of the coast. Having tracked its birth and approach, we must now confront the heart of the chaos, the instant of disintegration. This is the realm of microseconds and millimeters, a domain studied with ultra-high-speed cameras filming at over 100,000 frames per second. The data from these studies is not just visual, it's quantifiable pressure, temperature, and acoustic data that paints a picture of controlled insanity. The moment the thin, leading edge of the wave, called the toe, touches the rock, a phenomenon known as air entrainment begins. The rock's surface, especially if jagged and porous, is not smooth. It traps a thin layer of air. The impacting water compresses this air cushion to a fraction of its volume, heating it instantaneously. This compressed air seeks escape, jetting out through cracks and fissures in the rock at supersonic speeds, a process that contributes to the rock's weathering by a mechanism called quarrying, where pressure from trapped air and water can actually pry off rock fragments simultaneously. The main body of the wave wraps around the rock's protrusions. CFD simulations show the development of massive shear forces. The water in direct contact with the rock slows to a near halt due to friction, the no-slip condition, while water just millimeters away is still moving at full speed. This velocity gradient creates intense vorticity, spinning the water into toroidal vortices, donut-shaped rings of turbulent flow that detach and drift downstream, carrying away energy and adding to the chaotic soup of the aftermath. But the most destructive and fascinating part is the cavity collapse. As the wave envelops the rock, it can trap large pockets of air. When the surrounding water pressure inevitably overwhelms the air pressure, these cavities collapse inwards. This is not a gentle squeezing, it is an implosion. The inrushing water from all sides meets at the center with such force that it creates a converging shockwave within the liquid. At the convergence point, pressures can spike to thousands of atmospheres, and temperatures can theoretically reach tens of thousands of Kelvin, albeit in a volume no larger than a pinhead, and for a duration measured in picosecons. This is the phenomenon of sonoluminescence, where light is emitted from these collapsing bubbles. In the churning maelstrom of a wave break, countless such micro-implosions occur, a fireworks display of extreme physics completely invisible to the naked eye. The sound generated is a broadband impulse, a sharp crack that contains frequencies beyond human hearing. This acoustic signature is used by scientists to monitor coastal erosion rates as the sound spectrum changes with the rock's morphology. The jaggedness amplifies all these effects. A smooth, rounded boulder would produce a more coherent, sliding splash. A jagged rock acts like a collection of sharp obstacles, each one triggering its own micro version of this violent process. Miniature toe impacts, air entrainment sequences, and vortex shedding events all out of phase with each other. This is why the resulting spray is so asymmetrical and wild. It is the superposition of dozens of these micro-impacts. The roar is the sum of their acoustic emissions. Furthermore, the salt water itself is a chemically active agent. The immense pressures and temperatures during cavity collapse can cause water molecules to dissociate, creating transient reactive species like hydroxyl radicals. These can react with mineral surfaces, accelerating chemical weathering. The data from mass spectrometers analyzing the aerosol plume post-impact has detected traces of ions not present in the bulk seawater, suggesting brief, localized chemical reactions of extraordinary intensity. So, the breaking wave is not merely a hydraulic event. It is a thermochemical acoustic one. It is a factory for extreme conditions, generating fleeting pockets of stellar temperatures, immense pressures, supersonic jets, and reactive chemistry, all wrapped in the deceptively simple package of spray and foam. This transforms our understanding of the scene from a macroscopic display of power to a microscopic laboratory of plasma physics and fluid mechanics happening en masse for free on every rocky coast on the planet. It is a demonstration that the boundaries between different fields of science, geology, chemistry, physics, acoustics blur completely in the face of nature's raw, unscripted experiments. Let's pull back from the microscopic and consider the witness you. The human perception of this event is a masterpiece of neurological and psychological interpretation, and it is almost entirely divorced from the physical reality we've just described. Your brain is not a high-speed camera or a hydrophone. It is a prediction machine built for survival, and it processes the wave crash through a series of shortcuts and filters. The first filter is temporal. The critical phases of impact, the toe touch, the cavity collapse happen in less than 1/100th of a second. Your visual system cannot resolve this. What you perceive as a single, fluid motion is in reality a series of discrete, catastrophic events blurred together by persistence of vision. Your brain stitches them into a coherent narrative of crash because that is the most useful model for understanding. The sound arrives delayed. Light travels nearly instantaneously, but sound travels through air at about 343 meters per second. If you are standing 100 meters away, you see the impact about 0.3 seconds before you hear it. Your brain automatically syncs them, creating the illusion of simultaneity, but this too is a constructed reality. The majestic slowness often perceived in sunset waves is another trick. The low angle of the sun casts long shadows and highlights the plume, while the eye is drawn to the large, sweeping arcs of the spray against the sky. This creates a psychological effect known as time dilation and awe, where emotionally potent, vast scenes seem to unfold more slowly. Your brain is allocating more processing power to the visual stimulus, making the memory richer and the perceived duration longer. The colors themselves manipulate emotion. The oranges and reds of sunset are long wavelength, low energy light associated with warmth, the end of the day, and often tranquility or romance. This colors literally and figuratively our interpretation of a violently chaotic event. We see powerful beauty rather than destructive chaos because our emotional response to the warm palette is positive. This is a profound psychological overlay. Furthermore, our sense of scale is often flawed. Without a clear reference object, like a bird or a person, rare in these shots, it is incredibly difficult to judge the true height of the wave or the size of the spray. A 3-meter wave can look like a 10-meter tsunami on camera depending on the lens and framing. This ambiguity allows us to project our own notions of sublimity, the awe mixed with terror that philosophers like Burke and Kant wrote about onto the scene. The wave becomes a metaphor for nature's overwhelming power, a symbol of purity and relentless force. Our brains are also wired for pattern recognition. The repetitive nature of waves crash, retreat, crash induces a mild trance-like state, lowering stress hormones and activating the default mode network associated with introspection and mind wandering. This is why people find it calming to watch. The reality is a violent, unpredictable explosion, but the perceived pattern soothes us. The original organic data from neuroscience studies using EEG and fMRI shows that watching waves activates the parietal cortex, involved in spatial reasoning, and the amygdala, which processes emotion in a unique harmony. It's a blend of attempting to comprehend vast space and experiencing emotional awe. So when you watch that sunset wave break, you are not observing physics. You are experiencing a carefully constructed illusion authored by your own brain, using the sensory input as mere raw material. You are seeing a story of power, cycle, and beauty that has been edited for coherence, emotional impact, and personal relevance. The actual event, the insane microviolence, the imploding bubbles of star-hot plasma, the supersonic air jets, is lost to you, replaced by a majestic, slow-motion ballet of light and sound. This disconnect between reality and perception is perhaps the most fascinating layer of all. The wave break is two events, one in the physical world and one in the theater of the mind, and they bear only a passing resemblance to each other. Finally, we must synthesize these threads: the hidden physics, the distant origins, the microviolence, and the perceptual illusion, to understand the true significance of this seemingly simple phenomenon. The wave breaking on the jagged rock at sunset is more than a natural spectacle. It is a Rosetta Stone for understanding energy transfer across scales, the relentless work of geological shaping, and the profound gap between objective reality and human experience. It embodies the principle of energy conservation in its purest form. Solar energy driving wind, transferred to wave potential and kinetic energy, converted into sound, heat, light, and the minuscule mechanical work of erosion, before finally dissipating as low-grade thermal energy into the ocean and air. It is a closed-loop demonstration of the laws of thermodynamics. From a geological perspective, this moment is a single frame in a film that is millions of years long. Each crash is a pixel of erosion. Over millennia, the statistical sum of these explosive moments, guided by the rock's fracture mechanics and the wave climate, sculpts the coastline. The jagged rocks themselves are a testament to this enduring contest. Their sharp edges are the parts that have most recently resisted, while the smooth, underwater platforms are the parts that have slowly yielded. It is a dynamic, living landscape, not a static picture. Furthermore, this scene is becoming a critical data point in the era of climate change. Rising sea levels and increased storm intensity, predicted by IPCC models and confirmed by tidal gauge and satellite altimetry data, mean that the energy equation is changing. The fetch for storms may alter. Wave heights are increasing in many ocean basins, and the base tidal datum is creeping upward. This means the same rocky coast will experience waves with more energy, impacting at different tidal heights, potentially accelerating erosion rates in a non-linear fashion. Coastal engineers now use the very physics we've discussed, the number, shock pressures, vortex shedding models to design defenses, but they are essentially trying to out-engineer a process whose fundamental power is being amplified by global systems. The wave crash is thus a barometer of planetary change. And on a philosophical level, it stands as a permanent reminder of the limits of human perception and the beauty of scientific inquiry. It tells us that the world is infinitely more complex, more violent, more strange, and more wonderful than our senses evolved for the African savanna can ever directly apprehend. The true awe lies not in the postcard, but in the knowledge of all that the postcard conceals. It is in the understanding that within that serene glow lies a storm's ghost, a shockwave's recoil, a bubble's star-hot death, and a rock's patient atomic-scale surrender. This journey from the storm to the synapse is the real story. And this is why you need to be part of this channel. If this deep, original, data-driven excavation into a single, common natural event has changed the way you see the world, imagine what we can do with volcanoes, with black holes, with the human brain, with the fabric of reality itself. This is just the beginning. So here is your final, essential call to action. Don't let this be a one-time insight. Click the subscribe button and turn on notifications right now. By subscribing, you are not just getting more videos. You are joining a community dedicated to stripping away illusions, to finding the shocking, data-rich truths hidden in plain sight. You are ensuring that this journey of decoding reality continues. Hit that like button if this changed your perspective, because it tells me you want more of this deep dive content. Share this video with one person who you think sees the world superficially, and challenge them to look deeper. The waves are breaking, the rocks are waiting, and a universe of hidden wonders is happening right in front of us. Let's discover it together. Subscribe now.